continue with the second talk by the ETH Prize Winner, Pierrick Bousseau, and the title is Strong Positivity for the Skein algebras of the 4-punctured sphere and of the 1-punctured torus. Yeah, please.
Okay, so thank you very much for the opportunity to give a talk. So in fact, the talk will be based on a paper which just appeared on an archive today. So the main result is in low-dimensional topology. So the topic referring to the title is about low-dimensional topology, but somehow in a slightly surprising way, the proof uses in an essential way complex enumerative algebraic geometry. And this slightly surprising connection between low-dimensional topology and complex enumerative algebraic geometry is motivated by the existence of string theorizations of supersymmetric gauge theories. So I'll start by some cartoonish description of each topic. So for me, low-dimensional topology will be a study of manifolds in dimension 1, 2, 3, and maps and embeddings between them. So typically, we'll talk about knots and links. Complex enumerative algebraic geometry, it's about counting geometric configurations inside complex algebraic varieties. So a complex algebraic variety is some geometric shape defined by the vanishing of polynomials with complex coefficients. So the example we should keep in mind for this talk is a complex cubic surface. So you choose polynomial in 3 variables of degree 3 with complex coefficients, and you look to the vanishing locus of this polynomial inside C3, you will get a complex surface. So something of complex dimension 2, real dimension 4. And given such nonlinear object, you can ask, for example, does it contain lines? So objects defined by equation of degree 1. And it's a famous result of the middle of the 19th century due to Cayley and Salmon that if you take a complex cubic surface, or precisely smooth projective, it contains finitely many lines. And in fact, it contains exactly 27 lines. Okay, so here is some kind of real picture of what happens. You have some surface, which is some cubic surface of some quite nonlinear object, but it contains this straight line in finite numbers, in fact, in exactly 27 ways. And in fact, this more than 150 years ago result would be relevant for our talk today. Finally, when you have a gauge theory in general can have interesting dynamics, for example, from elementary grounds or quarks, they can form non-trivial bound states like protons and neutrons. And when your gauge theory is supersymmetric, you can often realize it inside string theory. And the point of doing that is that often the non-trivial quantum field theoretic dynamics of the gauge theory is realized geometrically inside string theory. So some other extra dimension of string theory give you some geometric realization of the dynamics of gauge theories. And it is how topics like low-dimensional topology or complex enumerative algebraic geometry play a role or are related to the topic of gauge theories. Okay, so here I'm saying something already said, but with slightly more detail. So the main result will be in low-dimensional topology, and it will be about positive basis for the Kaufman bracket Skein algebras of the 4-punctured sphere and the 1-punctured torus. And the proof will be based on the enumerative geometry of holomorphic curves in complex cubic surfaces. And the proof is motivated by the existence of dualizations in string M theory of a specific supersymmetric gauge theory, the n equal 2 supersymmetric SU2 gauge theory with 4 hypermultiplets in the fundamental representation. So in this talk, I will focus on the first part, the low-dimensional topology story, essentially because it is where I think the main result is, and also because it's a more elementary topic to describe. So in this talk, I will focus on this topic starting from the beginning, and only at the very end, I would say a few things about algebraic geometry and the connection with physics. Okay, so I'll start at the beginning. We'll talk about knots. So a knot in a manifold is a connected, compact, embedded, one-dimensional submanifold. So essentially a cycle embedded inside your manifold. And the link in the manifold is a disjoint union of finitely many knots. Okay, so in this picture, you have links made of 2 knots. And we'll need the notion of framing of a link. The framing of a link is a choice of a no-wave vanishing section of its normal bundle, or in a more elementary way, each cycle component of your link, you view it as a boundary of some annulus. So each of the cycle making the link, is secant into some annulus. And because we are doing topology, we'll consider all these notions, knots, links, and framings up to continuous or smooth deformations. So up to isotopies of the ambient manifold. And as you probably know from, I guess, everyday life, knots and links are especially interesting in dimension 3. So we'll fix some oriented stream manifold M. And once you have a stream manifold M, you can look to all possible links, or more precisely frame links inside them. And from them, you can construct an algebraic gadget called the Kaufman bracket Skein module, which are introduced by Priestley and Schreif at the end of the 80s. So you look to all possible isotopic classes of frame links contained in your manifold, and you just take the free module over them, where you take module over the base ring, which is a ring of Laurent polynomials in a variable A with integer coefficients. So you just form a big vector space with a basis given by all possible links.
How is it? A is what was Q in the previous talk, right?
A big A equal Q to the 4.
Oh, okay, okay.
I mean, with my conversion with Q, which is maybe not the same conversion as in the previous talk, but the conversion I prefer is big A equals Q to the 4. Or in fact, it is the other way around. Q equal A to the 4, sorry. Q equal A to the 4, sorry. Sorry. And okay, everything will, okay. You can have a minus if you want. And in fact, at the end of the day, all.
So you're saying Q plus Q minus 1 is the unknown. It's usually Q plus Q minus 1 is quantum.
Then I think for historic Kaufman, I think it's really like that.
Yeah, exactly. But then you need minus for Q.
Okay, there are many possible. Yeah, it's correct. Okay, so you take this basis of links and you divide by scalar relations. So if you have 3 knots, which outside the small ball are identical, and in the small ball they look like these 3 pictures, then these 3 knots are related in your Skein module by this linear relation. And if your knot, or your link is a link union some unlink unknot, then you can remove this unlink unknot to the process of multiplying by this coefficient in your base ring. And in this picture, it makes sense if you view the framing as going towards you from the board. Okay, so this thing is the definition of the Skein module. You look to all possible links and you divide by quite natural looking linear relations. So for example, the Skein module of R3 is simply free of dimension 1, so it's a base ring itself. And so the thing which is essentially obvious is that it can be at most that, because if you have a link in R3 up to isotopy, you can make really close to some plane, and then you can resolve all the crossing with respect to this plane using the first relation, and then you just get a bunch of unknots and you use the second relation to evaluate what remains. And what is slightly not obvious is the fact that this thing is non-zero, but essentially it follows from whatever. There's a classical Rademacher theorem in that theory. Okay, so the Skein module of R3 is just the ring itself. In particular, if you have a framed link in R3, you can look to its class in the Skein module. It's just a polynomial with integer coefficients, and which is called the Kaufman bracket polynomial of the frame link L. And this Kaufman bracket polynomial is essentially equivalent to the maybe more famous Jones polynomial. So Jones polynomial is about unframed link in R3, and Kaufman bracket polynomial is about frame link, but the two can be related in some explicit way. And so essentially what we'll be talking about is Kaufman bracket Skein module is the generalization of these objects going from R3 to more general 3 manifold. We'll focus on 3 manifold which are a product of a 2 manifold by an interval. So surface times the interval. And in this case, your module, your Kaufman bracket Skein module, has a natural algebra structure. If you have 2 links, L1 and L2 in this 3 manifold, you can define their product essentially by placing L1 on top of L2. More precisely, L2 is in this product. Up to isotopy, you can assume it is in the surface cross -1, 0. You can assume L1 up to isotopy is in S cross 0, 1, and you just take the union of the two. And in that way, you get an associative algebra. It's obviously associative if you put three things on top of each other, and it's in general non-commutative. And maybe I've not written, but this algebra is known to be a quantization of the algebra of regular function on the SL2C character variety of the surface. And so I will call that the Skein algebra of the surface, even if it's the Skein modulo of the three-manifold surface cross the interval, because everything is determined by the surface. Okay, so we'll continue a surface of finite type. So the complement of finitely many points L inside the compact-oriented two-manifold of genus G. And essentially, we'll be able to reduce all the discussion from the three-manifold to the surface. So on the surface, we can talk about multicurve. Or a multicurve is a union of finitely many disjoint, compact, connected, embedded one-dimensional submanifolds. So again, just a bunch of cycles drawn without self-intersection on your surface, such that none of them bounce disk in your surface. And you can view such curve on the surface, obviously, as a link in the threefold surface called the interval, and in fact as a frame link, because you can take the framing parallel to the interval direction. And so why do we introduce this multicurve? Because there is this nice theorem which tells you that isotopic classes of multicurves form a basis of the Skein algebra as a module. So somehow it's a kind of generalization of the statement that the Skein algebra of R3 was just one-dimensional. It's clear that if you have a link in the surface cross interval, by projecting on the surface and resolving all the crossing and eliminating the things bounded disk, you get a multicurve. So it's clear that multicurve generate the Skein algebra as a module. And the thing slightly non-trivial is that in fact there are no extra relation between them, and so they really form the basis. So for example, let's look to the surface to be the closed torus. In this case, isotopic classes of multicurves are in bijection with this set B of Z, which are pair of integers up to a global sign. Essentially, a multicurve is determined by its homology class up to sign. And so for every P in this set B of Z, there is gamma P, the corresponding isotopic class of multicurves. And you can check that this multicurve has GCD of Mn connected components. And so a special case of the theorem before, this set gamma P is the linear basis of the Skein algebra of the closed torus. So as a linear object, it's something quite explicit. So each time you have an algebra with a basis, you can talk about structure constants of the product with respect to this basis. You take two elements of the basis, you multiply them, it's still an element in your algebra, so you can expand it on the basis, and the coefficients are called structure constant, and they live in the base ring. So for the Skein algebra, they live in this ring of polynomial, Laurent polynomial in A with integer coefficients. And now we are off to essentially the main topic of this talk, which is the notion of positive basis. We say that the basis of the Skein algebra is positive, is a structure constant of the product in this basis. A priori, they are polynomials with integer coefficient. We say the basis is positive if all these integer coefficients are all positive. There is no sign in the structure constants. And I just explained you that the Skein algebra as a natural basis is the basis of multicurve. So maybe the first obvious question is the basis for multicurve positive? So let's do some computation. Let's do gamma 1, 0 times gamma 0, 1. So this thing is essentially just some curve like that, and this one is some curve like that. So these two curves have only one crossing on the torus. So if you apply one time the Skein relation, you get this formula. So here the structure constant has big A and big A inverse, which have coefficient 1. So this thing satisfies the positivity condition. But if you just look to the next example, gamma 0, 1 times gamma 2, 1. So these things are two curves on the torus, which have two intersection points. To make this computation, you apply the Skein relation twice, and you get the following formula. So here you have plus sign, but here you have minus signs. So the conclusion is that, in general, the basis of multicurve is not positive. That is essentially almost the simplest possible example. Take a torus, take curve crossing in 2 points. It's not positive. So here you could just stop, or you could opt that maybe there is some other bases which are better positivity property. And so we'll talk about these other bases called the Bracelet basis. And you need a bit of algebra to define it. So we introduce Tn of x, some Chebyshev polynomials defined by the following formula. T0 is 1, T1 is x, T2 is x squared minus 2, and then Tn plus 1 is xtn minus Tn minus 1. And they are exactly the polynomials, such that if you write x equal lambda plus lambda inverse, then Tn is lambda to the n plus lambda to the minus n, if n is positive. And essentially, we'll twist the basis of multicurve by these polynomials. So what does it mean? If you have some isotopy class gamma of multicurve on the surface, you can write it uniquely in the algebra as gamma 1 to the n1 times gamma r to the nr, or gamma 1, gamma r are distinct isotopy classes of coordinating multicurves and edge are integers. So your multicurve is just a bunch of cycles, and you just put together the cycles which are isotopic. So there are n1 cycles which are isotopic to gamma 1, and r which are isotopic to gamma r. And then you define a new element in the Skein algebra, T of gamma, in this way by applying T of n1 to gamma 1, dot 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 T of r to gamma r. So you see, if the Chebyshev polynomial Tn was just x to the n, T of gamma would just be equal to gamma. But because Tn is x to the n plus subleading terms, T of gamma is gamma plus extra terms. So the set of this T gamma in general is different from the set of multicurves. In fact, this thing is again a basis, and it's so-called Bracelet basis of the Skein algebra. So let's go back to our example of the closed torus and of the simplest example which was not working, gamma 0, 1, gamma 2, 1. Now let's compute the T version of that. And you can use it. Here you only need to use the fact that T2 of x is x squared minus 2. And somehow the negative terms we had in the previous formula are somehow absorbed in the negative sign which are in the definition of T2. And at the end of the day, you get simply this sum of two terms with coefficient of a minus 2 and a squared. And so in particular, now we get something positive. So in this elementary example, we check that this T of gamma seems to have better positivity property than the basis of multicurves. And it's a general conjecture due to Dylan Thurston that for any punctured surface, this bracelet basis should be positive. So what do we have evidence for that? There is this theorem of, again, Thurston, which is that if you set a equal to 1, then it's true. So if you set a equal to 1, your Laurent polynomial becomes simply integers. And in this specialization, it was proved that structural constants of this bracelet basis are positive. And the second piece of evidence, which was known before, is that if you look to the case of the closed torus, the example I was discussing before, it was known from an conjecture that, in fact, the formula we saw in the example, in fact, is true in general. If you take P1, P2 in this set BZ parameterizing multicurve on the closed torus, you always have this very nice formula. The product of two elements is a sum of two basis elements, and the coefficients are just the power of A, which are in particular positive. And furthermore, the case of the sphere minus 0, 1, 2, or 3 points is essentially obvious. You can really just check it. So these cases are obvious. The case of this story about the closed torus is already not obvious at all. In a very concrete way, you have two curves on torus. They can intersect in many, many points. So to compute the product, you need to apply the Skein relations many, many, many times. It's not completely clear what you get at the end of the day. You get something maybe complicated. And the claim is that after rewriting it in terms of this Chebyshev polynomial, everything simplified in this very simple formula. Again, so the main result of this talk is a claim that the conjecture is true in essentially the next cases, which are the 4 punctured sphere and the 1 punctured torus. So I say that if you have less than 4 puncture on the sphere, it's obvious. So 4 puncture is somehow the first non-trivial case. And similarly for the torus without puncture, it was known before. It is non-trivial result. And we will generalize it to the case of 1 puncture. And so unlike the case of the closed torus, there does not seem to exist a simple closed formula for the structure constant of the bracelet basis in this case. So it does not seem like you can prove this theorem just finding a nice formula. You need to do something else somehow. Okay, so here maybe I should stop because this thing is some of the main result, and now I'll talk about how to approach this question. So are there any questions? Yes.
Why positivity is important? Why should
Okay. So maybe first naive answer is that if you have something positive, it's just nicer. But maybe a kind of deeper fact is that if you have positivity in general, it's considered as indication of existence of a deeper algebraic structure. If you have positive numbers, for example, you might want to interpret them as dimension of some vector spaces. And so I think it's part of conjecture of this business that this scan algebra should have some kind of monoidal categorification. And so this Bracelet basis should have some categorical lift, and if this categorical structure exists, it should imply positivity. So if you want, you can think of this positivity as some indication that this higher algebraic structure should exist.
Maybe
Yes.
I have another question. So how is it if you have a sphere with 4 punctures and 1 puncture torus? Is the perspective then to blue or other surfaces, or not really?
I've been naively thinking about that, but I did not say. I don't know. I guess I don't know if it's possible to do that. My naive impression was probably no, but I don't know. Okay, so the case of the 1-punctured torus can be essentially deduced from the case of the 4-punctured sphere. So from now on, I will focus on the 4-punctured sphere. So on the 4-punctured sphere, among all possible curves that you can draw on the 4-punctured sphere, there's the one which are really easy, which are so-called peripheral curves, which are just a very small curve around the puncture. So for each puncture, you have the corresponding curve, which is a very small loop around the puncture, A1, A2, A3, and 4. And this curve lives in the center of the algebra. They commute with every one else. And so you can view the scan algebra as a module over this bigger ring, where you take A1, A2, A3, A4 into the base ring. You can just work relatively to them. And now the curves which are really interesting are the multi-curve on the 4-punctured sphere, which do not have peripheral connected components. And you can check that the set of these interesting curves are still in bijection with this set B of Z of pair of integers up to a global sign. So we already saw this set as parameterizing multi-curves on the closed torus. And now I'm telling you that they parameterize multi-curve on the 4-punctured spheres without components, simple components around the puncture. And this thing follows from the simple topological fact that you can view a torus as a double cover of a sphere branching in 4 points. And from this topological relation, you can get this description of isotopic classes of multi-curve, of interesting classes on the 4-punctured sphere. And so essentially, this set parameterized by this set BZ is the basis of the scan algebra as an R module, so versus bigger ring. So essentially, it's enough to consider structure constant between these elements. So this T operation applied to these particular multi-curves. And essentially, the idea of the proof is to write down some algorithm which will compute the structure constants. So I say this algorithm will be relatively complicated, so it will not really be a closed formula, it will really be some kind of algorithm, but such that the final positive properties are manifest. And this algorithm will be based on combinatorial and algebraic notions of things called scattering diagrams, broken lines, and theta function, which were first introduced in the context of mirror symmetry by people like Concevic-Sommermann and Gross-Siebert. So these objects themselves come from your symmetry or algebraic geometry, but the objects themselves are purely algebraic or combinatorial, and I will be able to say what they are in a completely elementary way. It will only be in the proof that this algorithm is doing the right thing that I will need somehow to go back to algebraic geometry. But for now, I'm just describing you what this algorithm is looking like. So again, our elements are parameterized by this set B of Z, and you want to see B of Z are set of integral points into some set B, which is simply R2, so pair of real numbers now divided by plus minus 1. So you can think to such a thing simply as some upper half plane where you identify the real positive axis with the real negative axis. So it's some kind of space with some orbifold point of order 2 at the origin. And on this upper half plane, you can draw a so-called scattering diagram. For us, it's just data, for every line of rational slope in the upper half plane, you attach to it a power series into some variable. And roughly these variables keep track of the direction of the ray. So if the ray has primitive direction mn, then you attach to it a power series into the variable x to the minus m, y to the minus n. Okay, so this scattering diagram is just a bunch of countably many power series that are just think as being attached to various rays. And the particular variable inside each power series is related to the direction of the ray. Okay, so just a bunch of power series. And somehow the claim of the story will be that if this set of power series satisfies Na's condition, it's possible to construct an algebra out of this data. And this algebra is defined in terms of so-called broken line in this picture. So if you have all these functions attached to all these possible rays, then given such data, you can look to so-called broken line. So broken line is like this red thing on this picture. It's some continuous line in the upper half plane, which is made of linear pieces, except at some point it can break. And it ends at some point, and it starts from somewhere at infinity, and it bends finitely many times. And the condition is that it's bending only along rays of rational slope. And furthermore, these various linear pieces are decorated by monomials, where again, the power of this monomial is related to the direction of the linear pieces. And we say that this thing is somehow a nice broken line if each time the thing is bending, the monomial after and the monomial before and the monomial after are related by the function attached to the ray. Or precisely, if you have a monomial before and the function here attached to the ray, you roughly do something like monomial times function to some power, you expand, and the following monomial has to be one of the monomial of this expansion. And furthermore, the sum of the initial monomial at infinity is given. It is z to the direction with coefficient 1.
Sorry, when you say one of the monomial, doesn't have to be the leading monomial of the power series?
No, so in general, when you have a broken line arriving at a power series, on the ray, you take this monomial times the power series, and you expand, and you have many, many possible choices of monomials. And this one just has to be one of them, so it's not uniquely determined. When a line arrives on the ray, in general, there is several choices of how the broken line can continue. You just pick one of the possible monomials.
But we always talk about monomials, multivariable monomials.
Yeah, that's always monomial in this multivariable sense. Yes, exactly. Okay, so the point is just, it's something, if you have this collection of power series, writing all possible broken line is just some combinatorial algebraic questions. So here I wrote a bit more details for what is exactly this operation that you do with monomial and power series, which maybe looks a bit complicated, but essentially because of this big A story, big A variable, but roughly it's like the monomial, this function, and you take essentially product of this function, but some of this product is twisted by this variable big A. But it's a purely explicit algebraic thing. And now if you give yourself P1, P2, and P3 points in this B of Z, and if you take P upon Q, and if you take a point Q close enough to the P, then you can define something which looks like a structure constant, P1, P2, P of Q, which is obtained by taking all possible pair of broken line gamma 1, gamma 2, where gamma 1 starts with the direction P1 from infinity, gamma 2 starts with the direction P2 from infinity, and both gamma 1 and gamma 2 end at the same point Q, and at the final point Q, the sum of the two directions is the direction P. And you look to the monomials attached to this broken line as its final points, and you just take the product, twisted by, again, some power of A. So this thing just, so you look to all possible broken lines, satisfying some condition, you read off their coefficients, and it's define you this thing which looks like structure constants. And now you say that your scattering diagram is consistent if, first of all, this quantity does not depend on the choice of the point Q, and furthermore, if you define a product using these numbers as structure constants, you get some associative product, which apparently is not obvious at all. So the claim is that if you attach to the various rays random power series, you can always define these quantities, but in general, they will not they will not satisfy these two properties, and so you cannot construct associative algebra from them. But if these conditions are satisfied, then you get associative algebra, which come with a natural basis theta p by construction, called basis of theta functions, whose structure constants are given by this kind of formula in terms of broken lines. So now the idea is to construct a consistent scattering diagram. So if it's consistent, you can look to the corresponding associative algebra, and to prove that the resulting algebra is a scatter algebra we care about. And such that this natural basis of this algebra coincide exactly with this Bracelet basis of the scatter algebra. And so if you can do that by construction, the structure constant of this basis are given by this kind of formula in terms of broken lines. And so if you are able to control the positivity of this broken line, it will give you the positivity of this Bracelet basis. And because these broken lines are determined in terms of bending along the rays, this positivity will be essentially determined by positivity of the function attached to the rays. So if you know something about this explicit scattering, if you know enough positivity from the function attached to the rays, this positivity will transfer through the bending to positivity of the broken line, and at the end of the day to positivity of the structure constant of this algebra. So the idea is that you should really think to this broken line business as some kind of algorithm which will compute the broken line you care about, the numbers you care about. And here is just some explicit scattering diagram. So maybe it looks a bit complicated. So for every ray of rational direction, so for every mn co-prime, I should give you some power series. In fact, it only depends essentially of the pair of integers mod 2, and this power series, in fact, is given in terms of explicit rational function, which maybe looks slightly complicated, but which is this rational function. And so at this point, it's completely unclear why you should write these rational functions. But the claim is that I do that. And somehow the first theorem will be that this thing is consistent. And as I told you, if you pick something random to define your scattering, it will not be consistent. So, which is saying that somehow there is something special about this strange rational function. And once you know it's consistent, then the second part of the theorem, as announced, is that in fact you can construct an isomorphism of the resulting algebra with scatter algebra matching the basis, and then you can deduce from that the positivity. So essentially, once you know that the thing is consistent, the comparison of this algebra with scatter algebra is essentially computation in algebra. If your scattering diagram is given explicitly, you can make enough computation with broken line to match the description of this algebra with some known description of this algebra by generators and relations. And you can match the basis by matching some explicit PSL to Z actions that you can define on both sides. So this thing, there is some work, but it's essentially algebra. Whereas the first part is consistency. Après, it's again some algebra problem. You have a bunch of explicit power series attached to some rays. You define this structure constant by drawing broken line, and you want to prove that the resulting product is associative. But I don't know how to give algebraic proof of this fact. The only I know how to prove this thing is to use geometry, and it is where algebraic geometry is coming in. And some of the point is that there is a natural source of consistent scattering diagram coming from enumerative algebraic geometry. So if you have Y, a smooth projective surface over complex numbers, and do a normal crossings anti-canonical divisor on it, you can do enumerative geometry. You can count curves. So you can count genus G holomorphic curves in Y of a given homology class with this condition of meeting the divisor D in a single point. Technically, these numbers are example of Gromov-Witten invariance. And then you can use these numbers to cook up power series, and then you can use these power series to construct scattering diagrams. And here some of the neutral point of the story that some of the geometric origin of this number will guarantee that the resulting thing is consistent. So here I take that as a black box. I will not have time at all to say why this thing is true, and it uses part of the work I did previously with. Here I just take it as a black box that if these numbers are some geometric origin, the resulting thing will be consistent. And now we can just apply it cubic surface. And as I told you at the beginning, this thing has 27 lines on it. And it was already known to Cayley that on such surface there is 45 configuration of triangles of lines. So 3 lines for intersecting, forming a triangle. So you take D to be such triangle. And then the general geometry tell you that from counting curve in this geometry, you can cook up some scattering diagram d of yd, and the theorem is that the thing defined geometrically is exactly the thing I wrote down explicitly. And yet you do not have to guess the explicit rational, like the explicit formula I wrote down. You just compute, solve the geometric problem, and you see what you get. And you get the formula I wrote before. And in the simplest possible case, you need to count lines in this geometry. So there is 27 lines in the cubic, 3 of them for the triangle, and you want to count the other which intersect D in some points, so there are 24 remaining ones. In fact, you can check 8 of them intersect each side of the triangle in 1 point. Somehow this 27 story is somehow used for the simplest possible case of this computation. Okay, so yeah, the point is there is this completely different looking source of consistent. Apparently, this thing naively has nothing to do with Skein algebra. You count curve in this geometry, and the upshot is this consistent scattering diagram. And it just happened that if I look to the algebra defined by this consistent scattering diagram, it is a Skein algebra we cared about at the beginning. And I will end by a very short description of why this connection between this algebraic geometry question of counting curve in cubic surfaces and this Skein algebra, why they should be related. And even if it's not used in brute proof, it's like a strong motivation for the thing I just explained, which come from string and M theoretic realization of gauge theory. So here I will be extremely quick. So you can look to the following gauge theory, the n equal 2 supersymmetric SU2 gauge theory with 4 hypermultiplets in the fundamental representations. So it's one of the most studied n equal 2 supersymmetric gauge theory. And you can realize this theory as the so-called class S theory. So by looking at some 6-dimensional superconformal field theory, which is a theory living at low energy after decoupling gravity on 2 M5 brane. And if you go from 6 to 4 dimensions, so this thing is in 4 dimensions, and you go from 6 to 4 dimensions by compactification of the 4-punctured sphere. And so in this realization of this theory, the 4-punctured sphere is scalarized there. And then you can show that the Skein algebra, in fact, as a physical realization, has some algebra of line operators in the 4-dimensional theory. But then you can do something else. You can look to this cubic surface Y with this triangle of line D, and like use a complement of it. It's a non-compact hyperkähler manifold. And you can show that after some hyperkähler rotation, it is some elliptic fibration with a D4 elliptic fiber. And then you can obtain a different construction of this gauge theory in M theory by taking M theory on the 11-dimensional background Minkowski space times this hyperkähler 4 manifold time R3, with some M5 brane on the Minkowski space times the elliptic fiber of this elliptic fibration. And from this point of view, you can argue that the holomorphic curves that you are counting in this cubic surface geometry are physically realizing M2 branes which determine the so-called BPS spectrum, so part of the set of particles of the theory. So the claim is that there is 2 different realizations of this gauge theory. In one of them, you get line operators in the gauge theory related to the Skein algebra. In the other, you get a set of particles in the theory determined by these holomorphic curves. So what remains to understand is why the set of line operators and the set of particles should be related. And this thing was essentially done by Gayotomo and Nelsky, which explain that line operators are so-called low infrared expansion in terms of so-called frame BPS states. And this expansion has some wall-crossing phenomenon. And this wall-crossing of this infrared expansion are controlled by BPS states. So a very first approximation of what is happening is that you have a line operator, you can attach to it a particle to get a new line operator. It's a kind of basic phenomenon. And then, so most of what's happening is some kind of translation in the physics context scattering diagram. The function attached to it are essentially encoding the BPS spectrum of the theory. The broken lines describe the frame BPS states. And the fact that you get 27 is 3 times 8 plus 3 recovers some 8, which is well known to play a role in this theory. So here I should end by saying that, in fact, this translation between the object I introduced, scattering diagram, broken line, and physics objects has not been fully done, and it certainly is not done in full details in my paper. And certainly, I mean, it has not been done, and it should be. It will be interesting to do it, in particular to investigate the most general version of the conjecture. But for the purpose of my talk, the story was essentially some motivation for this connection, why this question in algebraic geometry should play a role in solving this positive question for the 4-puncture sphere. And while you know that it should be true, it's much easier to prove it. Okay, I'll stop there. Thank you.
Well, thanks a lot. Any questions or comments?
Yes.
So maybe, can we say once again, so the scattering diagram is a finite set of rays?
In fact, every ray of rational slope appears.
Every ray of rational slope appears, so scattering diagram is the rule to associate with power series.
Yeah, that's right. So there are infinitely power series which are just indexed by MNN coprime.
And you say if you have, say, cubic surface, there is a canonical scattering diagram associated to that specific power series to each direction.
Yeah, that's right. And so geometrically, so the direction of the ray has to do with, so we are counting curve in the cubic surface with contact order, in fact, with tendency condition along this triangle of lines. And this direction of the ray has to do with the contact order of the curve. So yeah, maybe. Okay, so you have a triangle.
Because it's kind of roughly the torus, right? The boundary divisor. It's the canonical. This I think.
Yeah, but for example, so you can curve meeting one side of the triangle. It's like one possible direction. But then you have curve going to the corner of the triangle, and here you have all possible tendency condition on one side or the other. So you have like 3 cones. And this upper plane is a union of these 3 cones, which are dual to the side of the triangle.
So I guess in other ways, this is the kind of, we'll look at the punctures of the anticanonical divisor, which is elliptic curve, more or less, right?
Yeah.
This is just what homology realizes there.
Yeah, exactly. Yes?
So, is there a nice reason why the Chebyshev polynomials appear? Some kind of property of them which makes them.
From which?
The bracelet basis.
Yes.
From Chebyshev polynomials.
Yes.
Chebyshev polynomials to those gammas.
Yes.
So why Chebyshev? Why Chebyshev polynomials?
So first, something a bit more concrete that Chebyshev polynomial, there is this fact that Tn of lambda plus lambda inverse is like just lambda to the n plus lambda to the minus n. So Skein algebra is a quantization of the character variety. And essentially, this object of gamma at the character variety level, it simply is a trace function of a power. So if you apply when I wrote, where is it? Whatever, if gamma is connected, and if it's and if you have k copy of these isotopic classes, then Tn of gamma is trace of the representation of your fundamental group on this element to the power k, trace of the element to the power k. So from this, let's say, representation theoretic point of view, it's a quite natural thing to do. But from a more, yeah, and I think in fact I'm slightly confused about this question from a physics point of view, which has to do with to the existing natural basis of these algebra of line operators, and I don't know. But something something else I could say is that I am explaining you that you can compute this product using these pictures. So if at some point I claim that this picture computes this Bracelet basis, the Chebyshev polynomials somehow should appear from this picture. And in particular, you can recover the closed torus from punctured torus by essentially forgetting one punctured. And essentially, in this operation, is the case where all the functions of the scattering diagram all become 1. They all become trivial. And so it's a case where broken line cannot bend somehow. And now if you want to compute the product of 2 elements, so let's say you have a broken line coming from somewhere and coming from somewhere that are just tracked. But because of this Z mod 2 monodromy here, if you have a straight line there is another straight line on the other side. So just this elementary picture gives you the sum to product formula in the case of the closed torus. And essentially, it gives you the recursion relation for the similar argument gives you the recursion relation for Chebyshev polynomial. If in the simplest case you want to compute the contribution of n0 times 1, 0, so they're just horizontal things. So you have two horizontal things and you want to compute the product. You see, you can either put them on the same side. So it's like T1 times Tn is Tn plus 1. Or you can take one on one side and the other on the other side because they're identified by the sign. So you get exactly the recursion relation for Chebyshev polynomial. Just look from drawing this picture in this orbifold. So no.
Thank you.
So does this relation to algebraic geometry give you some candidates for this categorification that you were talking about?
In the way I presented it, no, because I do the counting in the world of Gromov frequency, where things does not really categorify well. But if you add some kind of sheaf counting version of these counts that you expect, it should produce something like the categorification that you want. But this kind of categorical count of sheaf with this kind of tendency condition are not well developed yet. So far, no, it does not solve this question.
Risha, you have another question?
Yeah, maybe if I can return to the definition of the scattering diagram. So you see the power series which associated to those arrays, so they are counting of closed curves. So here you look at the... So
the way I phrase it in my honest algebraic geometry is a closed curve in Y meeting the divisor D in one point. But intuitively, you should think about them as open curve with boundary on the Lagrangian torus, which fibers the complement of
this is exactly where I'm confused, because also your broken line have this point which kind of suggested that there is the end point inside.
So the function of scattering as a scattering diagram are defined by counting curve in Y meeting D, but the broken line.
Closed one. Functions closed. And for example, for cubic surface, it's always positive, this power series.
In fact, the explicit thing I wrote as a positive expansion. Sorry. Yes, he's saying if you expand as positive coefficients, integer positive coefficients.
I mean just from defining, because there's a counting of some closed parts inside of the surface.
Except they are like virtual countings, as usual in Gromov frequency. And in fact, the naive numbers can be rational and can have signs. But to define this function, you form power series, but you take some exponential, and there is some kind of slightly miraculous constellation, which makes the final thing of integer coefficients. But it's not completely obvious just from the geometry.
Not on the rational, but integer positive coefficients.
Yeah, that's the function integer positive coefficient, but some of these numbers come from the true count of curve are really rational with signs, but they are combined in some nice way, so that at the end they have a positive integer. But indeed, it's true that some of the broken lines should correspond to kind of open curves, which end in the middle. And because I'm an algebraic geometer, I don't know how to define them. Because it's open, I don't know how to define at the virtual level. I don't know how to define them, but somehow in my story, I do not use the enumerative interpretation of the broken line. I only use the enumerative interpretation of the rays, and then I define the broken line in a combinatorial way. But indeed, you expect it to correspond to open curves.
I see. So the rays correspond to closed curves, but broken lines are kind of holomorphic disks or something.
Yeah, that's right. So in some symplectic languages, the ray of the scattering are like Maslov index 0 disk, broken line are like Maslov index 2 disk. And then it's a usual word crossing for this kind of disk.
Maybe we should postpone the further discussion to the coffee break. Thanks again and congratulations.